Graph the following. All right, so in example A, we have f of x is equal to 2 to the x power minus 1. What you want to do when you graph an exponential function is identify some key components. One of the things you'll need to know is where the intercepts occur. Another thing you need to know is where the asymptote occurs in the graph. And then finally, you'll need to know generally where it's increasing and where the function is approaching the asymptote. So what we want to do that is to kind of think about the nature of exponential equations or functions. Let's start with some simple points here. -2, -1, 0, 1, and 2 plugged in for x. And what I want to do is just think about what that's going to do to the term 2 to the x power. We'll forget the -1 just for a moment here. Let's start with, for example, if you plug in for 2 to the x, what if you put in 2 to that? Well, that's of course going to give you 4, right? And then of course, if you subtract the 1 from that, you're going to end up getting 3. So when you plug in 2, you're going to get 3. And of course, you know that 2 to the third would be 8, and 2 to the fourth would be 16, and so on and so forth. So it generally grows as you put in positive exponents. It's going to get bigger and bigger and bigger and bigger. So that's an interesting thing to note. Obviously, it means that as you move along this direction of the x-axis, the graph is going to get larger and larger on the y-axis. So that means the graph will generally be increasing. So that's useful. Let's talk about what would happen if you plug in 2 to the -2 power then. Well, remember that when an exponent is negative, in order to make it positive, you have to take this sort of fraction and reciprocate it. And what that's going to do is it's going to bring the exponent down below the fraction bar, and when it crosses that little line, the sign of the exponent changes. So remember that little poem, cross the line, change the sign of the exponent here. And in that case, it'll be 1/4 or 1/4. So the negative exponents actually make the value of the statement smaller. And of course, you subtract 1 from the 1/4 like we're doing here, because if we have 2 to the x minus 1, if you subtract the 1 at the end, you'll end up with -3/4, right? But what's more important here is just the general idea that if you put in negative exponents, the size of this term will get smaller and smaller. For example, what would happen if you had 2 to the -1 power? If you had 2 to the -1 power, you'd have ended up having 1/2, right? And that's only a half. It's not as small as the 1/4 was, right? So the more negative the exponent becomes, like -10, for example, is going to make a very small value, whereas -1 is not as small. And of course, if you have 2 to the -1 being 1/2, and then you subtract the 1 away from it, you're going to end up with -1/2. That's how we'll get -1/2 here for -1 in our table. And then of course the other ones, you can just plot some points for those. So what would it be if you put 0 in? Well, it'd be 2 to the 0 minus 1. So that's going to end up giving you 2 to the 0, which is 1, then -1 gives you 0. And then if you have 2 to the 1 minus 1, of course you'll get 2 minus 1, which is just 1. All right, so those are your points. All right, before we plot these points, let's identify the asymptote for the function. All right, the asymptote is going to be found by basically looking at this term 2 to the x and thinking about the fact that, as we mentioned, if we put in really small values for x, right? Values like -1,000, -1,000,000, -1,000,000,000. It's going to make this a very small fraction, right? Imagine if you put in -1,000. It'd be 2 to the -1,000 power, right? Which would end up being 1/2 to the 1,000th power, right? This number is almost 0. It's very small, right? So the reason why I mention that is because if that were 0, then what's the smallest value the function could ever achieve? Well, if f of x is equal to 2 to the x minus 1, and I'm saying this could eventually get so close to 0 it would virtually be 0, that we could just get rid of that and call it 0, then it means the minimum the function will ever be is -1. All right, so remember, this guy can never get negative, though. 2 to the x can never be negative. All it can do is get smaller, like in terms of getting closer to 0. So the reality is, if it was 0, then the minimum would be -1, and that is your horizontal asymptote. Now, it'll never actually reach that asymptote, right? It doesn't actually ever touch there, because as we mentioned, no matter how big the exponent is, it's never going to give you that 2 to the x is 0. But it'll get so close to that at some point, we will not be able to tell the difference between it and 0. So for that reason, we have that asymptote, and the graph will certainly hug that asymptote. With that asymptote in mind, and then looking at the values that we can plug in here, we should be able to plot the function. So let's go ahead and put -2 and -3/4 in the drawing. So that's kind of, maybe right here. And if we do -1, -1/2, that's here. And then if we do 0, 0, of course, that's at the origin. And that is, by the way, the x and y intercept for the function, right? And then we'll have 1, 1. So that's the point here. And then we'll have 2, 3. So 2, 1, 2, 3. And that's a few points. That's enough to go ahead and plot the functions. So we'll connect and get a graph that looks something like that. Let's do that a little smoother than we did before, so it looks a little better. There we go. All right, so there's our graph, and that's basically the graph of the function. Now, from there, we can just mention something about the domain and range here. I would like to just point out that the domain is all real numbers for this function. There are no restrictions, right? We don't have a fraction where we could have a 0 in the denominator. We don't have a radical where we could have something negative underneath the radical. So there's no restrictions on what we can put in for x. So the domain is all real numbers. Any number on the x-axis is fair game. The range, as you can see from our discussion about the asymptote, is going to go essentially from -1, but not including -1, as we said, all the way up to positive infinity. That graph is shooting upwards forever on the y-axis, right? So this would be your domain and range. We have the asymptote, we have some points, we have the plotted graph. We're done with that problem. Let's look at part B then. So looking at part B, we have something similar. We have 3 to the x minus 2. But for this graph, basically, they're taking something that would otherwise have looked very similar to the one we had before, but they're moving it over. Now, our original graph of, say, f of x equals 2 to the x, right? Let's look at that. If we had a graph that was just like f of x is equal to 2 to the x, it would have actually looked like this. When 0 would be plugged in for 2 to the x, you would end up getting what? The value 1, right? So at 0, you would have had this point here, and then it would have climbed. 2 to the 1 would have given you 2, right? So 2 to the 1 would have given you 1, 2 on the axis. That would have been here, and then it would have gradually hugged this line. So it would have been something like that, right? So this would have been the graph of 2 to the x. If you had 2 to the x minus 1, you're just going to take this intercept and move it down one place. The minus 1 just drops the graph, and everything shifts lower. So we ended up having something like that, right? So that was our graph that we ended up with in our last problem. All right, so that dropping the graph one step lower occurred because we had this minus 1 at the end of the function. In this particular case, we're doing something a little bit different. It's f of x is equal to 3 to the x minus 2. So what's happening here is that you're putting the subtraction inside where the exponent is located. This is kind of comparable to the parabola. Remember the parabola, we had something like x squared, it meant the function opened like this, right? But then if you change the graph by throwing a minus 1 at the end, it opened one step lower, like from there, so the vertex dropped one step down, right? But then if you did something a little different, if you instead put the minus 1 in here, do you remember what that did instead? That actually changed the graph from being the original graph of this to being one step over to the right. So for example, that meant that we moved the vertex over like that, right? But basically the graph didn't shift up, it shifted to the left or right because we were kind of inside the parenthesis joining this -1 with the x, right? It's the same sort of thing that's going on in this exponential function. In the exponential function, the minus 2 here is sort of attached with the x, right? So what that means is that we're actually going to be moving the graph to the left or to the right 2 units. But just like it was for the parabola, when it's happening up there, we're actually going to move in the opposite direction you would think. So minus 2 is not going to move us to the left 2 units, it's going to move us to the right 2 units. So all the points will be shifted to the right. All right, so let's talk about some points and then we'll get the asymptote, the domain, and range. Okay, so let's talk about some points. Let's do -2, -1, 0, 1, 2 again if you want. We don't have to use these particular points, but we can use them. Actually, if you wanted to, we could actually, since we know everything's going to be shifted 2 steps to the right, we could actually change this list, right? If we know we're going to be shifted 2 steps to the right, let's move all these points 2 steps to the right, right? So instead of doing -2, let's do 0 there, right? So we'll add 2 to each of these. So we'll do 0 there. And instead of doing -1, let's make it +1, right? Instead of doing 0, we'll do 2. And instead of doing 2, we'll do 3. And instead of doing 2 here, we'll do 4. All right, so it's the same thing. We just shifted everything over by 2, right? So we added 2 to all our x points. And this will allow us to get the general look of the graph and have the most important points for the problem. So let's put 0 in. What happens if you get 3 to the 0 minus 2? Well, that's the same as 3 to the minus 2 power. And this is what I was talking about. This now looks like as if we just plugged in -2, correct? And of course, that'll be basically the same as 1 over 3 squared. So 1 over 3 squared, or 1/9. That's the answer for that. Or if we plug in 1, we're going to end up with 3 to the 1 minus 2 power. That's the same as 3 to the -1 power. And that, of course, is 1/3. And if you plug in 2, you'll have 3 to the 2 minus 2 power, or 3 to the 0 power, or in other words, 1. If you plug in 3, you'll have 3 to the 3 minus 2 power, and you'll end up with 3 to the 1 power, and of course that's just 3. And then finally, if you do 3 to the 4 power, it'll be 3 to the 4 minus 2, or in other words, 3 to the 2nd power. 3 squared, of course, is 9. All right, with those points, we should be able to go ahead and plot the graph. Before we do that, though, I just want to talk about, again, the asymptote for the function. So that little minus 2 is not going to really change a whole lot in terms of the asymptote, right? So what does the 3 to the x minus 2 have for a horizontal asymptote? Well, regardless of what you put in for x here, no matter how small you make the x value, right? If you make the x value, for example, negative 998, then you're going to have what? 3 to the negative 998 minus 2, or in other words, 3 to the negative 1000 power, right? Which is going to be a very small number because it'll be 1 over 3 to the 1000th power. So again, this is going to be very close to 0, but that's all it's going to do. It's never going to get less than 0, right? It can't go negative. The smallest it can ever be is 0. So that means the asymptote is actually the x-axis, or in other words, the place where y is equal to 0. All right, so I'm going to draw a little kind of dotted line here to indicate that that's where our asymptote is. Okay, after that, let's go ahead and plot some points. At 0 on the x-axis, you have 1/9, right? So not a very big number. Let's actually go ahead and put some points here too. 1, 2, 3, 4, and we'll do 1, 2, 3, and then 1, 2, 3, 4. Okay, so that's good enough. We don't really need many more places than that because we're not going to use those. But if I have 0 and then 1/9, that's a very tiny place. That's right here maybe, right? And then if I have 1, 1/3, so at 1, we're going up a third. So it's kind of hard to draw the difference between 1/9 and 1/3 by hand, but there it is. If I go 2 and then 1, I'll be here. And then 3 and go up 3, we'll have 1, 2, 3. That'll be here. And if I go up 4 and then 9, now we're off our little chart there, but you can kind of imagine maybe it's up here somewhere. I don't know, maybe there, just for smooth numbers. And let's go ahead and connect those dots for our graph. And that's basically it. Remember, it hugs this x-axis forever, right? So that's your graph of 3x minus 2. So basically, it's the original graph of 3 to the x moved 2 places to the right because of that minus 2 that's up in the exponent.